There is nothing wrong with your television set. Do not attempt to adjust the picture. We are controlling transmission. If we wish to make it louder, we will bring up the volume. If we wish to make it softer, we will tune it to a whisper. We will control the horizontal. We will control the vertical.
Below a huge plastic balloon of helium gas, a man prepares to explore the fringes of outer space. He is Major David Simons, a U.S. Army doctor. To his shaven chest, a stethoscope is fastened. For one object of the adventure is to test human endurance many miles above the Earth's surface. It will help to answer the question, when we achieve space travel, will the human body be able to stand it? The pressurized canister, with its mass of lightweight instruments and its bright aluminum casing to protect him against radiation, is sealed around Major Simons. He plans to stay aloft for 30 hours or more, gathering information on cosmic rays and other problems, and incidentally, admiring a view of the world such as no man has seen before. As the miles slip past him and the atmosphere thins out, the plastic balloon will swell into a sphere. Major Simons' achievement, a flight of 32 hours, reaching an altitude of about 19 miles. He was tired and cramped, but he came to no harm. Thus, a brave soldier scientist takes mankind a step farther in his journey into space.
At Cape Canaveral fires a Thor rocket with a sensational payload, a balloon as big as a 13-story building. This canister released from the rocket carries within it an Echo balloon satellite, like the one that will reflect signals from space back to Earth when put into orbit next fall. Remarkable cameras carried aloft by the Thor record the brief life of the largest satellite yet, as it goes 922 miles into space. The experiment is a complete success.
NASA's been using balloons for science research for over 30 years. The exploration that can be done on balloons is continuing to grow. Balloons are low cost, and traditionally we get our payloads back. So you can work on a technology development where you're testing something, getting it back, recover, refly again. The standard balloon that I fly is about 660 feet long when it's made. So when it's inflated, it's over 400 feet tall by 440 feet wide. Think of a dome stadium. That's how big my balloons are. We use helium as our lifting gas for our balloons. Helium is lighter than air. So the mass of the air it displaces is greater than the mass of the balloon plus the mass of the helium. How we get it to go up is we have to put extra helium in the balloon on the ground. That gives us a positive upward force for the balloon system to rise through the atmosphere. And once the balloon actually reaches the float altitude, then that extra helium we put in for the lift is vented out. Now, when I have the balloon at float altitude, one of the things that's important is temperature. A balloon is a thermal vehicle. If I have the sun go away, my gases will cool and my balloon will start to lose lift. Our 40 million cubic foot volume balloon can lift up to 6,000 pounds. That's like 1.5 Ford Explorers. Imagine picking up Mom's SUV and launching it into the stratosphere.
I'd rather have a science balloon than a science satellite. With a balloon, there's no need for rockets. To get a satellite to hover over the same spot on Earth, geostationary orbit, you have to be 36,000 kilometers away, too far to use some sensors, like radar. A balloon can sit 1,000 times closer in the stratosphere, 30 to 40 kilometers above the Earth, and still be above 99% of the atmosphere with clear views of the stars or wide panoramas of Earth. You can bring down a balloon, tinker with onboard scientific equipment, and then launch again. Satellites, not so much. Cost is also a factor. NOAA's 4 new geostationary weather satellites are estimated to cost $11 billion, whereas a balloon flight might cost just a few $100,000. NASA's been flying balloons for a long time, but without any steering capabilities, they drift in the wind across continents. Now, private industry is getting in the balloon game, with new technologies that are enabling balloons to hover over one spot. These balloons rise and fall in the stratosphere, catching countervailing breezes that allow them to stay roughly in the same place. How do you keep a balloon stable enough to use a telescope? Gyroscopes can help keep a platform pointed at its target, even as it sits in a twisting gondola.
We are just like a cell phone tower, but in the sky. And the same way that their central office of the telco interacts with all their cell towers, they will interact with our balloon. Another way to think about it is, if you drive down the highway on a phone call, you will switch between cell towers. What we're doing is kind of flipping that on its head. So you're standing still on the ground with your LTE phone. And as one balloon goes overhead, another balloon comes in range, and you're switching between one balloon to another without dropping the call. The balloons today can cover 5,000 square kilometers on the ground.
What you're seeing is a balloon inside a balloon. We have a unique way of actually adjusting the altitude in these balloons.
This balloon has a constant volume, and there is helium in it, right? So the helium brings the balloon up. And now, if we want to change altitude, we have another balloon inside the balloon that we fill with air. And as we add more air in there, the mass is going to increase and the balloon is going to go down.
It's easy to steer the balloon by picking up different winds and different wind directions at different altitudes.